official. Just discuss the potential topics within the group and with each member, and you can just potentially come up with anything. But since they are there, since the common interest is already there, so since, I mean, like, yeah, like different groups probably have different interests, and different modalities are of interest to everybody. So I'm gonna spend about 30 minutes or so introducing some very representative papers that address or handle different modalities of EHR. So one paper is about text classification. Another is about dealing with EEG. EEG is what? It's an electronic encephalogram or something. It's about measuring brain waves, but so it's a time series data. Basically, it's a sensor data, and it's measuring different frequencies. And the same principle can be applied to ECG, electrocardiogram, 심전도. So that there's a paper called SleepNet, which handles EEG signals. So I'm going to briefly introduce that paper as well. And the third is what is the third? The third is the images. So I'm going to introduce two seminal papers. One is about recognizing diabetic retinopathy, and another is I think it's skin cancer. So both one is from Google, one is from Stanford. So 4 papers, I guess, or 3 modalities. And the another final paper is about handling structured codes or sensor data. So the line is pretty blurry between structured codes and sensor data, because sensor data is already kind of like coded. So, all right, so let's get to, I guess we can start off with the last one, which is written by Professor Zach Lipton from CMU, or is he in CMU? Yeah, give me just a second. All right, I'm going to share my Google Chrome. All right, so I hope that if anybody has problems seeing the shared screen of mine, please, yeah, give me a ping. So the paper is called "Learning to Diagnose with LSTM Recurrent Neural Networks." This is probably so it's a general approach. This paper aims to diagnose 12 or 16 different diagnoses or ICD-9 diagnosis codes, and this is one of the very first papers that applies LSTM network. So LSTM is a variant of RNN. So RNN, there are 2 variants. There's GRU, gated recurrent units, that we talked about, and there is LSTM which we also covered. So 2 different variants of RNN. So this is the very first paper that applied our LSTM to diagnose more than just a specific disease. Previously, before this, there were some couple of papers that use either some form of RNN to diagnose a specific disease. In my case, heart failure. Some other case, there were like kidney failures or Alzheimer's. But this paper is one of the very first papers that tries to diagnose multiple number of diagnosis codes. All right, so this probably might be helpful to okay, I see. Okay. Anyway, so this can be probably very helpful for the team number 4 whose common interest is structured codes. But generally, this is a very general approach. So, and this is very similar to what we are doing now. I mean, what the attendees, the participants of this class is doing now with assignment number 3. So I'll just briefly go over this paper and then move on to the next one. So, as I said, so the goal is to have a, okay, so they are given, they're using 13 frequently but irregularly sampled clinical measures. So, and oh, they're classifying 128 diagnoses, which is probably a lot. So, okay, so it was my mistake to call out like 12 different diagnoses, because this is using 13 different measurements. So in chart events of mimic3, there are hundreds of different types of measurements, and I guess we are using like maybe 300 to maybe 500 different, is it 500 or maybe 1,000 different like different measurements in chart events. We were using, so the item IDs represent each and different measurement. Here in this paper, they're taking 13 of the most frequently but irregularly sampled clinical measurements. So 13 most frequently measured are typically O2 saturation levels, 산소 포화도, heart rate, respiratory rate, blood pressure, what else? Temperature, something like that. So that already covers like 10. So anyway, so based on those 13 measurements, they're trying to classify 128 diagnosis codes. So the model architecture is very simple, very similar to what we're doing now in assignment 3. By the way, they are not using mimic3. They are using their own data set, which is collected from University of LA, Children's Hospital of LA. So we'll go right into the architecture. So this is it. This is very simple. So the X's are the different measurements sampled irregularly. So right now, what we're doing with assignment number 3 is also irregularly sampled data, because we're crawling through the chart events, and chart events are typically irregularly sampled. So you don't measure, for example, you don't measure temperature every 5 minutes or every 10 minutes or every 20 minutes. You measure temperature whenever the nurses or the doctors feel like it, well, like when it's necessary. Same goes with heart rate, respiratory rates, O2 saturation level. I mean, typically some measurements are regularly sampled because you have like machines hooked up to you. Like O2 saturation levels can be measured by having a clip on your thumb, which is called pulse oximeter or something. So there's like a small clip that goes on your thumb, and that kind of measures the O2 saturation, how much like oxygen you have in your bloodstream, basically. So those kind of things are all like electronically collected every like 5 or every 10 or maybe even every minute. And so some are regularly sampled, some are irregularly sampled. Here, the author is assuming that everything is irregularly sampled. So there needs to be some way to embed the temporal information, which you all need to do basically when you're using chart events, because chart events, you have timestamps, you have item IDs, you have value numbers. So it's exactly the same in this same setup as this paper. So the way they train their network is a bit different from ours. So in our case, this is how we train the network. So we put the irregularly sampled measurements into the LSTM, and based on the last time step or the hidden layer of the RNN from the last time step, that becomes the patient representation, and then you use the last hidden layer to make a prediction whether the patient will die within the hospital or not. But in this case, this guy, what they do is they continue, like they make the same prediction at every time step for like extra performance boost. So even if before the final time step, like given the first measurement, Zach predicts whether the patient will die or not, then again, given the second two time steps, makes the same prediction, and does that all the way till the last time step. So this is kind of like a multitask learning, or kind of like auxiliary prediction task, something like that. So you just make the model make the same prediction so that it is more robust to like different time steps. This is kind of probably the strategy that all of you can employ for a very small change of your source code. This is kind of like maybe couple of lines of change of codes, basically. And you'll probably get like an extra, I don't know, 1% or 2 for your AUROC or AUPRC. All right, so yeah, auxiliary output training, we won't go with that. So I think they did a lot of different, like a lot of comparison between different different baseline models or ablation studies. But basically what they're saying is that LSTM outperforms MLP, which is a single hidden layer neural network, or logistic regression, or base rate, which is just frequency-based methods. So compared to these very simple classical methods, LSTM like outperforms. Even LSTM, even their method outperforms ones that use rather feature engineered LSTM. So like here, they're using 13 different variables. So, but when they're using MLP with expert features, that means that like a doctor was sitting side by side with the first author, or maybe with an IT engineer, and the doctors gave information like what kind of features they should come up with and put into MLP to get the best outcome or best performance. And well, I mean, compared to just putting everything into the MLP, compared to that, having an extra feature performs way better than just dumping everything into the model. So feature engineering is still relevant. So if anybody's like, I don't know, I guess nobody has a medical degree in our group, but if there were, then they would have a significant advantage over other groups of people. So compared to dumping everything into the MLP using expert feature, like there's a significant boost. But even compared to that, just dumping everything into LSTM outperforms the expert features of MLP. So there's a lesson there. Okay, so yeah, among the 128 different diagnoses goes, some diagnosis performs better, like gets better performance compared to others. So for example, diabetes mellitus with ketoacidosis. So some specific diabetes. So it is way more predictable than acute respiratory distress syndrome or delayed milestone. Delayed milestone. Okay, so this is not a diagnosis code. This is just the code that comes along with ICD-9. So it's not exactly an ICD-9. Or neoplasm brain unspaced. So like cancers are really hard to predict because you don't see the symptom until the very late stage. Typically, like stage 4. That's when you really see the symptom. So until then, you really don't. It's really hard to know whether this patient has a cancer or not. And acute respiratory distress. So anything that is acute is hard to predict. Acute means 급성. So acute respiratory distress syndrome means like 급성 호흡 증후군 or something. So if anything is to happen abruptly, means that it is very hard to predict. Compared to that, chronic diseases are way more predictable because they tend to persist over a very long period of time. So like diabetes is typically it's a chronic disease. So chronic means 만성. So 만성 신부전 이런 것들은 굉장히 뭐 항상 걸리는 거, 항상 있어. 한 번 걸리면 계속 걸리니까 이제 굉장히 예측하기가 쉽죠. 그래서 so yeah, some diseases are easy to predict, some diseases are not. So focusing on something that is more difficult to predict is also a very like valuable task to do, but which often requires significant amount of domain knowledge. So yeah, some tasks are just not doable only based on EHR. Like would you be able to predict whether the patient will like some kid will break their bone by playing soccer or playing basketball? That is utterly impossible to predict. Some are just random events, and some are just for some events the resolution of information incorporated in the EHR is just not enough. You need to turn to like wearable data or image data, like images or MRIs or something like, or even like genetic information, like your DNAs. So ultimately, we need to go multimodal. We want to collect as much information as possible from the patient, even maybe relying on like KakaoTalk, like chat records and Google Map, search history and all that. Like those are very, very relevant to your daily routine. So someday maybe people will voluntarily give up their personal information to have more like high quality healthcare, like healthcare by AI. Maybe someday, like such day will come. I don't know, but not within like 5 years. I don't think so. Anyway, so this is that paper. So if anybody's interested in like using structured codes, this is a very like one of like this like yeah, I guess you can learn a lesson or two from how they pre-process the data and how they fill the missing data and all that. I think those like pre-processing information is in the appendix. Learning curves per diagnosis results. Or not. Okay, that's weird. Give me just a second. Let's see. Right here, okay, so the data description. So the third section is where they describe how they pre-process the task. So it is not a trivial task, that is a meaningful task like we do with the current mortality prediction, where we use only the first 3 hours to predict the patient who dies after the 24 hours, so which is a challenging task to do. They do something very similar. So episodes vary in length from 12 hours to several months, but they only take the first 24 or first 12 hours or something. It's like, yeah, this paper is like already 4 years old, so I don't remember all the itty-bitty details. But anyway, so I want to announce that all the papers that I reviewed today, I will post them on class someday, so people who are interested can look them up. So 2016, so it's a very like it's a long time ago. All right, so the next paper is, should we go to the images? I actually have a presentation for that. All right, give me a minute or two. All right, I found it, but let me just tweak it a little bit to make it a bit more interesting. New share, Microsoft. All right. All right. Can everybody see the slides that I just shared now? Is anybody still seeing the Google Chrome web browser? Oh, we have one more participant. Interesting. All right, we'll deal with it later. Anyway, so I'm gonna assume that everybody's seeing this, seeing the PowerPoint slides. All right, so well, officially, I haven't gone through like CNN, convolutional neural nets during this class, but I'm gonna talk about the images. So before I do that, I'm gonna like cover very briefly what the concept of ConvNet is. If you're already familiar, you can just, I don't know, do something else for like 5 or 10 minutes. All right, so basic methods. So the thing that I'm gonna introduce today is called this one, dermatologist level classification of skin cancer with deep neural networks. So this one came from Stanford. The diabetic retinopathy, so which is what is diabetes in Korean? 당뇨. 당뇨성 망막염증을 예측하는 거. 그러니까 trying to predict diabetic retinopathy. That is done by Google, guys, and that was published in JAMA, which is like one of the very top, most prestigious medical journals. This one came from Stanford, and it is published in Nature. So this is like the same level of like impact, social impact, scientific impact. Anyway, so before we address that, I'm going to talk about ConvNet for about a couple, maybe 5 or 10 minutes. So ConvNets, I guess this comes from the philosophy of deep learning, but as I said, maybe I covered this during the first or second lecture. But the power of deep learning stems from 2 aspects, which is that first, it performs better. It just shows better performance. And second, you don't need to do feature engineering anymore. You just dump the images, and like before, in the classical era where you had to use like SVMs or random forest or whatever, some classical classifier to classify images, you had to come up with the feature set, which is typically like SIFT is what people use like back in early 2010s or like late 2000s. So in that era, in the pre-deep learning era, trying to classify whether this is a dog or not, in order to do that, you need to came up with a like a set of features. Like is there like what's the like a contour of the images? What's the color of the images? And if we're being more semantic, like are there eyes, or are there like tongues, or like are there like fur-like texture, something like that? Like you need to come up with your own set of features that the model should focus on. But well, in the deep learning era, we don't need to do that anymore. So we want the model to figure that out on its own. So like information like this, like is there furry ear? Is there like eyes? Is there nose? Is there tongue? Like these kind of information, we want the model to pick them up automatically. Oh, but we don't want to do that. We want to provide the image to the ConvNet, and we hope the ConvNet will pick them up. So in order to do that, it needs to like have a procedural like steps. So first, the model needs to focus on like local features. So when I say local, so this is like when I say global feature, that's like some information that you can gather by looking at the entire picture, like the entire picture. But when I say local feature, then it's something that you focus on locally. So like this is a nose, and this is a tongue, and this is an eye. And then once you have those local features gathered locally, then you want to sum them up, or you want to aggregate those information or combine those information to make the final judgment. Like given these local features, this entire image must be a dog or something. So ConvNet lets you do that. So as I said, you need to first start from the local features and build them up, build the features on and on and on and on, like on top of them, stacking and stacking. So first you need to gather the local features, and the way the ConvNet does it is by having a convolutional filter, or sometimes some people call it kernel. So typically people use a 3x3 kernel. Okay, here it's called kernel. So 3x3 kernel. So this is the entire, let's say this is the entire image. And this is, let's say it's not an RGB, it's a black and white. So you don't need 3 channel. If you have an RGB image, like red, green, blue, natural image, then your input becomes a 3 channel image. But if you have a black and white, then it's a 1 channel image. And 0 means like black, and 255 means white, like MNIST images. So let's say that this is a 7 by 7 black and white image, and 2s are like stronger, and 1 is like gray, and 0 is black. And in order to gather or collect local features, you first have a 3 by 3 kernels like this, which is randomly initialized. Here it has, the kernel has like 4000000 negative 4 as the weight value, but it is typically randomly initialized. And it is basically you multiply the kernel, the 3 by 3 kernel, to this region, 3 by 3 subsection of the entire image, and you multiply pixel by pixel. So 4 times 0 is 0. 0 times 0 is 0. You repeat that until the last like 9th element, which is negative 4 by 2, and then you sum them up, and then you sum them, and then you get a negative 8, because all the others are like either zeros here. There's like it's either 0 here, or it's either 0 here, except for the 9th element, which is negative 4 and 2. So you multiply them, you get negative 8, and then you sum all them up, and then you still get negative 8. So the aggregate signal or aggregate information from this particular region using this particular filter is negative 8. And you slide this by the, okay, we don't, okay, so you slide this filter along this axis. So you can slide to, let me get a pen. Right, so you can, the next time step you can have the same filter applied to this region, and then the next time step, like this region, you do this until you get to the until you, I see is there a noise coming from somewhere? All right, so until you get to the last region here, and then once you do that, you move to the next row. So then you start here, you do the same thing here, you go here, and then all the way. Also, you go like this way, and then you move down 1 row, and then you do this, repeat this procedure until you get to the very bottom here. And you can of course push through, and then have like maybe have the filter applied like this by having a zero padded region here. But it's kind of like it's up to the designer choice. You can do this or not. In order to, so you can assume that when you apply this filter like this way, and then let's say you don't go overboard. You stay within this particular like range. So if you do that, then how many values do you get? You get one value from here, 1, 2, 3, 4, 5, right? You have 5. You get 5 numbers. So you get 1, 2, 3, 4, 5 numbers here consecutively. But your original image was 7-dimensional. It was 7 by 7. But if you stay within the image of the strict boundary, then you get a 5 by 5 value, right? So if you don't want that to happen, if you want to retain the dimensionality, then you need to go overboard. So you need to start from here and then end here. I'm sorry, you need to start from here, and then end here in order to retain the 7 by 7 dimensionality, like this. But it's up to the designer's choice. And you don't have to use just one single filter. You can use like I don't know, like 10 different filters, like 10 differently initialized filters, or 20 or 64, 128, like as many filters as you want. But if you use too many filters, then your memory will blow up. So you need to have, that's also hyperparameter. Yeah, so you have, let's say you have you're using, I don't know, 10 different filters. So then you'll get 10 different sets of like convolved features like this. Like if you use 10 different filters, there will be 10 different like this, right? You can imagine there will be 10. And then there are a lot of different like post processes. You can do pooling, or you can do like, I don't know, 1D1 convolution. They're all like different like advanced techniques. Basically what you want to do is, so you started with one single black and white image, but you've expanded it into 10 different like feature maps. So because you are using 10 different filters, you are hoping that each feature map will retain different sorts of different types of image, different types of information. Then you somehow aggregate 10, or you somehow like retain the 10, and you can do the same. You can have another filter, another 3x3 filter, or maybe 5x5 filter, and then apply that to each and every 10 feature maps and blow it up into, like, I don't know, 20 different feature maps in the next stage. So this is one convolution stage, one conv. You can have another conv using another set of filters, and then you can repeat this process as many times as you want. So if you do that, then you get this kind of architecture. So apparently you start with a RGB input, so it's a car image with red, green, blue channel, 3 channels. You do a convolution, then you get like, so it was three channels, but now it has, I don't know, like 10 or 15 channels, and it's a slightly contracted. So maybe they didn't like go overboard. So you have convolution, you have the convoluted features, and then you do pooling. So pooling is some, I guess I can briefly mention what pooling is. So pooling is another way to drastically reduce the dimensionality of your outcome. So this is, let's say that you went overboard. So you went overboard. So you start from here and then you ended from here. So you are retaining 7x7, but you don't want to have the 7x7 dimensionality. You want to like project it into an even lower dimension, like maybe 3x3 or 4x4. So the way that you can do it is by having like a pooling. So pooling is that maybe so pooling doesn't require a learnable weight. So it's just a deterministic operation that you do on the feature map. So let's say if you're doing like 2x2 pooling, then just take 2x2 and then you take the maximum value out of the 2. So if, for example, if this was 2, 4, -6 and -8, then you take 4 out of this. So that's max pooling. So you do this for all the 2x2s, 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 and then you'll get like contracted feature map out of this. If you do like 4x4 pooling, then that is like a lot of contractions, because out of 16 elements, you're just taking one maximum value. So that's kind of like a very powerful or very crude, like you can call it either powerful or crude, like a very powerful way of decreasing the dimensionality. So that's max pooling, because you take the maximum element. There's also average pooling. So average pooling, you can imagine what average pooling is. You just take the average value out of the 2x2. So that will be like somewhere around like -2 or something. So pooling is, I'm not sure if pooling is often used in these days, but anyway. So you do convolution, then you get pooling. So you like decrease the dimensionality again. Then you do another convolution. You do another pooling. You repeat those processes again and again until you get a very, very contracted, very like lower dimensional feature map, but has way more channels than before. So before it was a very high dimensional image with 3 channels. Now it's, I don't know, like very low dimensional feature map with a lot more channels. Then you like lay them out in a very long horizontal vector, and then you apply a bit more fully connected layers, and then you finally apply softmax to get the prediction whether this is a car or truck or a van or bicycle. So this is the typical convolutional neural network architecture. And then recently there were tons and tons of different architectures, but the study that I'm going to introduce, the one with the skin cancer, they use something called, I'm sorry, this is not the one. They use something called InceptionNet. So InceptionNet was proposed by people from Google, and there are different versions. So Inception version 1, Inception version 2, Inception version 3. I think the skin cancer paper used Inception version 2. But basically, it's another combination of convolution and pooling. So you can see that there's an input image, then you have a 7x7 convolution. So they're using 7x7 filter. And they do pooling, and then they do something called some operation. Then they do conv some operation, then they do another pooling, and then they have like, it's a very complicated architecture. And people don't use InceptionNet these days very much. People use something called ResNet, which is residual network, which looks like this. So this is InceptionNet. This is InceptionNet, and I mean ResNet. And probably the major difference between InceptionNet and ResNet is that there's a skip connection. So you can see there's a connection between different convolution blocks. So there's connection here, here, here. So what happens here is that there's like another like highway or path where the feature map can go through. So before, the only way the feature map only way the input could go through from here to here is just following the convolution. But here, if the model thinks so, then the image doesn't have to go through convolution. It can just go through the highway without being convolved, basically. So like it's giving an alternative route, and it's a very robust architecture. All right, so this is the end of the ConvNet intro for the newcomers for 10 minutes. So is there any question related to ConvNets before I move on to the skin cancer study? Nope. All right. All right, so before I move on, let me just grab a cup of water. All right, so the study is called dermatologist level classification of skin cancer with deep neural networks. And I heard from somewhere that Sebastian Thrun was very famous for autonomous driving car. I'm not sure why he's involved in this, but anyway, so yeah, as I said, this was published in Nature 2017, and the high level description, the task description is that given a clinical image or skin image, classify whether this patient is suffering from something called keratinocyte carcinoma. So carcinoma is another type of cancer, or is it just some benign seborrheic keratosis? I don't know what this is, but basically it's trying to classify whether I'm sorry, give me so basically the task is it's a binary classification. So given a skin image, trying to classify whether this like image is caused by malignant cancer, 악성종양, or benign neoplasm. So benign neoplasm meaning 악성, 양성인가요? 악성, 양성. 하여튼 양성 종양. So basically something which can be seen as cancer or not. So it's just like some skin abnormalities. So there's like also another task is whether it's a malignant melanomas or is it a benign nevi. I don't know what nevi is. Nevi is some another type of like skin abnormality. All right, so try to see if you can predict. So one row is malignant and one row is benign. So try to see if you can predict whether you can correctly predict either this is benign or this is benign, or this is malignant or this is malignant. Do you think it's rather like clear that you can clearly distinguish between benign cases and malignant cases? In my case, I couldn't really see which is benign, which is malignant. But apparently, according to this study, machine can. So, so the answer is these were benign and these were malignant. So when you first see the images, like something, if you see something black, then you're like, this must be malignant, or this must be like more serious case of like skin abnormality compared to like a rather light toned like skin disease. But obviously it's not. But the machine can pick that up. So, all right, moving on. So as I said, they use Inception v3. So okay. So given a skin lesion image, the authors of the paper, they put it into InceptionNet and going through a lot of convolution pooling. So there's like average pooling, there's max pooling, there's concat dropouts, so like a lot of operations. And the outcome is, so the task is to predict whether something is either keratinocyte carcinoma or some keratosis, or if it's malignant melanomas or benign nevi. So basically, you just need to classify into 4 different classes. But instead of doing that, they trained the model to classify into 757 different types of skin diseases. So like all the whole different types of melanomas, whole different types of nevus. So nevi is probably a plural of nevus. So like 757 different types of skin diseases they predicted, just to try to have a more informed model. And then after this, they aggregate the predicted score into 4 different classes. So either it's, as I said, either it's this or that, this or this, or this or this. So yeah, it's kind of like a, I don't know, you can see this is a feature engineering. So yeah, and it's a bit more heavily feature engineered. So the way they predicted 757 different number of classes is not just like independently treating them, but they had a specific diagnosis hierarchy, or just like the one that I used in the Graham paper that I introduced a couple classes back. So there's a skin disease hierarchy. So on the very top there's skin disease, then there's like the second resolution is benign non-neoplastic malignant, and then if you follow benign there's dermal, melanocytic, like different, like more and more refined classes of skin disease. So you have this, and this 757 different classes come from this ontology, or this hierarchy. So these are not just selected out of the blue. It follows a very specific domain knowledge. And then aggregating based on the outcome, aggregating into the final prediction objective is also, it requires a lot of domain knowledge. So that's why this whole paper works so well, because the Stanford researchers work closely with skin disease experts, basically. And this is the outcome. So let me just to show. So they were doing 2 different tasks. One is carcinoma, one was melanoma. And the blue line is the specificity sensitivity. So is it? So this is recall. This is the 1 negative, 1 minus precision or something. I'm not really sure. Anyways, this is some curve basically. And yeah, okay, yeah, this some curve basically. And the red dots are the scores coming from actual dermatologists, skin disease doctors. So the blue line is the score coming from the machine, the Inception v3. And in both cases, both carcinoma and melanoma, it is outperforming, the model is outperforming typical dermatologists. So they are actual doctors. And the average score of the dermatologist is the green cross here. So it's kind of like a bar graph. So compared to the average score coming from the doctors, the blue line, the model is outperforming the average dermatologist. So which is very impressive. So that's why this was published in the Nature paper. All right. So this is the end of the skin cancer paper. So you could apply the same principle. So there are already a very well-known architectures that you can just borrow from GitHub projects like ResNets, wide ResNets, Get Inception. What other architectures are there? I don't know. There are like tons of architectures, but typically I think people tend to use ResNet 50 as like a classical, robust, high-performing model. Or you can use Inception B3. It doesn't matter. And then you can apply some domain knowledge here in the outcome stage to predict whatever you want. So, all right. Moving on to the SleepNet, which is handling the EEG signal, the brainwave signal. So, if any team is interested in dealing with ECG data or EEG data, this is the simplest approach that you can take, right? So SleepNet, of course, according to based on the title of the paper, you can assume that this has something to do with sleeping. So what this paper does is, so patients who are suffering with like sleeping, like they can't sleep well, or they tend to wake up very often during their sleep phase, or they can't have a deep sleep, or they can't have like a rapid eye movement sleep, like REM sleep. They come to the sleep clinic or to the hospital, and then doctors hook up the EEG device to their head, and then they let the patient sleep, and then doctors record the brain waves, like alpha waves or beta waves or gamma waves, something like that. So they use something called polysomnogram. And that's the objective of this paper is to label the outcome of the polysomnogram, PSG, and label them with different sleep stages. So, like, if you look at this, so they record a lot of stuff, and based on like different time segments, they want the machine to automatically label like, this region is REM stage, and this is like non-REM stage. This is like some other stage, and like this is some other stage, basically. So they want to do that. They want the machine to automatically label that so that the doctors can take a look at the outcome and qualitatively assess the state of the patients, like how like if the patient is having a quality sleep or not, basically. And the way the sleep networks is, unfortunately they don't have a spectrogram here. Interesting. All right. Okay. All right. I'm sorry. I think some information I'm missing from here, but basically, the sleep, the brain waves, the outcome of the brain waves, the left brain and the right brain, they are coming from 10,000 different patients, and it sums up to 80,000 hours of EEG data. So the 80,000 hours of brain waves with different frequencies, different channels. So there are 6 channels, and typically what people do when they want to analyze either EEG signals or ECG signals is that they apply a Fourier transform on the waves, the brain waves or the cardiac ECG signals, and they turn that into the spectrogram. So spectrogram, let me just pull up a very typical spectrogram here. All right, let me just share my Google Chrome a bit real quick. All right, so the signal that the SleepNet gathered is equivalent to this area. So this is ECG signal. So this is a 심전도 cardiac signal, but the same principle applied to brain waves, brain signals. So this is what you get from the raw data. So these are like different frequencies, like all the different frequencies all combined into a single like waves, but you can convert them to spectrograms. So here, this is a 2D image. So the x-axis, is typically a different like frequency. So when you apply Fourier transform, you can decompose a single wave into a set of waves, or basically a set of waves, and each wave has a different frequencies and each wave of each frequency has different amplitudes or different like strength. So that is why we have a two-dimensional output when you apply Fourier transform. So like this y-axis is the strength or the amplitude, and this axis is the frequency. So you can see that like this specific frequency has like this amount of like strength. So compared to this frequency wave, this frequency wave is contributing more to composing this very complex wave, basically. So what people do is they apply convolutional neural network on this 2D spectrogram, because this is two-dimensional output. So you can think of it as an image, and if you have an image, you can use ConvNet. So you can have like a filter of like 5x5 filter that walks across this two-dimensional spectrogram, and you can see that. So this is the ECG. So this is a cardiac signal. So you can predict whether a person is having different types of cardiac, like heart-related symptom. So like atrial fibrillation is, I think this is called in Korean 심세동 or something like that. 심세동 something. So it's like the heartbeat is like very weak or something. Anyway, compared to that, if you compare this to this, they have a very different pattern in the spectrogram, also compared to this. So you can assume that by applying ConvNet and like ResNet or InceptionNet, it can probably predict whether a given spectrogram is coming from atrial fibrillation or other rhythms or artifact. And same goes with SleepNet. So you can convert a brain signal and try to predict whether this particular segment is the patient is in REM stage or non-REM stage or something like that. So yeah, I guess I won't have to go into the architecture because it's just basically ConvNet. All right, so this is the end of the SleepNet. So if the reason that I'm going over the spectrograms thing is because there are a lot of free ECG or EEG dataset you can get from PhysioNet dataset repository. So let me go back to my Google Chrome. So here, I think I briefly showed you this webpage where this PhysioNet databases. So as I said, okay, I definitely did. So in the clinical database, there's EIC and Mimic, but if you go, there's a whole different section of all the ECGs that you can freely access. So if you're interested in sensor data or ECG data, or I think there is also EEG somewhere. All right, so this is non-EEG data set. All right, so here again, this is like something related to sleep studies. So definitely there's EEG signals. So each record includes 3 or more EEG signals together with EOG. I don't know what EOG is. Anyway, so if you're interested in EEG, you can definitely get it from this CAP sleep database. Everything is freely accessible as long as you agree with the data usage agreement. And this one's taking some time. Right, so there's probably data usage. Okay, this probably even doesn't even require data usage agreement. So you can see here directly, just you can download the data set. and then going to the whole ECG thing. So the MIT BIH dataset is quite often used by like people who want to study like heart diseases. So there's MIT BIH here. I think there are class 3 BIHs here. Yeah, here, MIT BIH atrial fibrillation database, long-term database, ventricular arrhythmia database. Arrhythmia is 부정맥, arrhythmia database. So a lot of like ECG dataset you can readily access. So if anybody's interested in dealing with time series or sensor data or ECG signals or spectrogram, you can definitely do that by going through all the ECG repository here, like whole different collections. All right, so, and of course there are images. So if anybody's, I think I covered the chest X-ray database. So there are chest X-ray database, but there's also just the images, JPEG collections. So depending on your needs and your interest, you can definitely get that. There is also MR, magnetic resonance angiography is probably Choyong's or something. So this is not MRI, so but this is some MRI-like image. But let me just take a look. How big is this? I think there are only like 75 different images here. Yeah, only 75. So it's not a lot. But the chest X-ray database has, I think, 200,000 different chest X-ray images. So if you're interested in images, I recommend that you take a look at this database. And you can apply Inception or ResNet or like any convolutional neural networks you want to predict something, basically. Or you can use, if you're familiar with machine learning, or if you're familiar with generative models like GANs or variational autoencoders, then you can maybe try to generate a synthetic chest X-rays, like using GANs or something. Right, okay, so is there anything else that I want to address? Oh, I'm sorry if I forgot to introduce one more thing. So this is called Camel. I forgot the name of the paper. Right, it's this one from NACL. All right, so this is again one of the very first papers that handles mimic-free note events, the text only, so only text. So what they're trying to do is based on the discharge summary. So in the note events, actually, it's probably better to go take a look at the note events. So note events table is where all the free text notes are contained. And there are categories and descriptions. Sorry, not forget out. Okay, yes, there's category and there's description and then there's text. So text is the actual text, like what the nurses or the doctors wrote. Category is like whether this is written by nurses or written by someone else. And description is like, oh, this is discharge summary, this is admission summary, something like that. So combining this two types of information, you can collect only out of like thousands and thousands of different notes, you can only collect the discharge summary. So discharge summary is what the nurses or the hospital administrators or doctors write when the patient is discharged from the hospital. So it contains the summary of the experience the patient went through during the stay at the hospital. So based on those discharge summaries, what this paper tries to do is trying to predict what the ICD-9 codes will be, and that ICD-9 codes are coming from here, diagnosis ICD. Diagnosis ICD table. So diagnosis ICD. So ICD diagnosis hierarchy or system was proposed for billing purposes. So in the first or second class, I talked about how the reimbursement works for hospitals and doctors. Like they have a report on like using the ICD-9 codes and using like procedure codes, medication codes, and diagnosis codes. They draft up the report and then they submit that to 심평원, and the 심평원 goes through the report, and based on the codes, they like pay the money to the doctor. So this particular table is for that purpose. When the patient is discharged from the hospital, they fill up, they enter the diagnosis codes list, billable diagnosis codes list to this table. So the diagnosis code list, so this table, diagnosis ICD, and the discharge summary from note events are tightly connected. They're one is dependent from the other, so they're highly dependent on each other. So that's why this paper is focusing on discharge summary to predict the outcome, to predict the set of diagnosis ICD-9 diagnosis codes. So and this paper is probably one of the very first paper that does that, using deep learning approaches, basically. I mean, there were non-deep learning approaches trying to do that, but this one uses deep learning approaches. And the test that I just described, based on like using the note, using the free text note to predict the ICD-9 code, that task is called automatic coding. So this paper is doing automatic coding not using RNN. Naturally, you would think that these people would use RNN because this is based on text, but they are actually using one-dimensional convolutional neural network. So let's see if they have a model architecture, and they're making it a bit interpretable. So which means that given a text segment like this, and the outcome prediction was foreign body in main bronchus. Main bronchus means like, so there's something in your lung, basically, or not exactly lung, but let's say, yeah, in your airway and in your lung, something is in there, like maybe you swallowed something, and so that was the predicted outcome based on this particular segment. And this bold type is the reason that their model predicted this. So it's kind of like interpretable model. So large mucus plug on the left of some, I don't know, some lung or something. So there's large mucus. So mucus being like 끈적끈적한 점성 물질, yeah. And compared to other models like cosine, like just simple CNN or logistic regression, you can also make them interpretable. Compared to that, their interpretable model makes way more sense. So the reason for predicting this is this, but when you use logistic regression, the high contributing words were entire left lung, which doesn't really tell you the reason why there is a foreign body in main bronchus. So this is a simple example. So they use convolutional neural networks, and do they have a model architecture? I guess not. All right, so let me just draw that real quick then. So the way they do it is, so there's a text segment, like there's one word, another word, another word, another word, another word, like this, another word. So this could be like, the patient suffers from chronic disease and coughs a lot, something like that. And then there's like, so if you have a sequence of tokens or word like sentence, then previously what ConvNet did with images is that there was an image and there's a ConvNet filter. That the filter was two-dimensional. So the filter was either 3x3 or it was 5x5 or 7x7, and you slide the filter like this and like this, and then all the way to here. So you slide and then you slide and then you slide. But this is two-dimensional approach because images are two-dimensional. You can do the same with one-dimensional text input. So here you can assume that there's a three-dimensional filter, convolutional filter, that slides along the one-dimensional axis. So there's 1, 2, 3 three-dimensional filter. So multiplied to the word embedding, multiplied to the word embedding, multiplied to the word embedding. You sum them up, and then you get a sum embedding values here. and then you slide the window here to here. So you do this again, 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 and then you get another embedding. Then you slide again, you slide again, you slide again, until the very end. Like you slide again, and then you get three. You get the aggregate embedding of the three embedding, 3 token embeddings, or 3 words. So you have like contracted, or like you have a decreased dimensionality. You started with how many, like 10, and now you get like 7 or something. Or to be more specific, if you had 10, then you'll get 8. And then you can have the same convolutional filter applied again, like 3 here, 3 here. You do the same sliding. You have another convolutional filter that slides like along this axis. So again, you get 1 here, 1 here, 1 here, 1 here. Now, starting with 6, you have 4 again, again, again. You can do that until you get a very one last embedding, or you can just aggregate these 4 into, or you can just like add these four embeddings and then get the aggregate. It depends on the designer's choice. And of course, just like there were a lot of filters, like people were using, even for one convolution, people are using like 10 different filters, or 20 different, or 64 or 128 different filters to get a lot of feature maps out of one, like a lot of feature maps here on another feature map, another feature map. You can do the same with one-dimensional convolution. Like you can have one set of convolution filter, another set here, like 64 different convolutional filters. So there will be like one here, again, another, like this basically. And then you do this again, 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 and then you basically you're contracting the dimensionality. So this approach is what this paper used. Instead of using RNN, they use CNN. The reason they did, I forgot why they did so, but it works pretty well basically. These days, people don't use RNN, people don't use CNN, people use transformer. So that's another sequence model. You can use transformer to do the automatic coding. Maybe that could be one of the potential project, like using transformer on top of node events to do the automatic coding, like intuitively. All right, any questions so far with the spectrogram, with the notes, with the images? Any question? So I just introduced these 3 papers because they were like the very representative, like seminal works handling different modalities. And of course, you can think about how you want to mix things up. Like if you have images and text, maybe you can use transformer for text and resonate for images, and somehow you need to come up with a like smart way to, you know, how to mix the embeddings. All right, so we have 10 more minutes. Actually, I wanted to finish my session for like earlier than this, and then have a breakout session for each individual teams to have like potential discussion. All right, so for a brief 10 minutes, I want everybody to go to their own like breakout room. I'll assign by the team, and have like a digestion time to digest what I've introduced right now, and think about the potential projects. Even maybe you can like stay longer if you want to, or you can just end with a very short discussion for 10 minutes and then have a follow-up session on your own. But let's just have a breakout session for now. And if you have any question within your own breakout room, just call me so that I can go there, and then we can have a discussion. All right, I'm going to stop sharing.